Here we're going to introduce waves and how waves work. This is especially important as we start our plant growth challenge and we are looking at how the UV lights work, the grow lights. In order to understand how those lights work, we got to understand waves because light travels as a wave. So a wave is basically just a repeating pattern. It's a disturbance that transfers energy without moving matter. Normally, when you transfer energy, you have to smash one thing into another, right? You smash one car into another, and that's going to move the second car in a different direction, right? You swing a baseball bat and it hits a baseball, and the baseball reverses direction and starts heading towards the outfield. But with a wave, there's no matter that has to be moved and has to collide, but you can still feel that energy in some way. So there's different parts to a wave. We have amplitude, wavelength, frequency, the crest, and the trough. So the amplitude is the height. It's this number 2. So on your paper, you should label that. That height of the wave corresponds to more energy, meaning a higher height carries more energy. And when we're talking about sound, amplitude is basically just turning up the loudness, right? So a higher wave will carry with it more energy. That makes sense when you're at the beach. Taller waves are the ones you want to surf, right? Wavelength, that's going to be number 1, right? So it is usually measured from the crest, which is number 3, the top of the wave, to the next top of the wave, right? And that would be the wave length. So basically what that is describing is how often the waves are crashing, which then gets us to frequency. The frequency is just the number of waves per second. So a higher frequency means that the waves are crashing more often. So if you're at the beach, rather than having one big wave every 5 minutes, maybe you're having one big wave every 1 minute, right? So that would increase the frequency. If you've got more waves crashing, you're going to have more energy, right? If you're standing in the shallows and you keep getting smashed by the waves, then you're going to feel that energy being transferred onto you, right? So a higher frequency also corresponds to more energy. Same thing with the wavelength. A shorter wavelength corresponds to more energy, because if we shorten this number 1 and the waves are coming more frequently, as the wavelength goes down, the frequency goes up. So what that means is if the distance between one crest and another crest is shorter, that means the waves happen more frequently. So shorter wavelengths cause more frequency, both of which cause more energy. The crest is the top of a wave, and the trough is down here at the bottom of the wave, number 4. So some examples here. If we look at something with short wavelengths versus long wavelengths, right? In this one here, we see that there's short wavelengths. If we were going to count this line here, the straight line is the same distance, it's the same length as this straight line. And we see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 waves in whatever distance that is, right? Here we only have 1, 2, 3, 4. So in order to have 4 versus 12 waves, that means the fact that we have 3 times as many waves here means that the frequency is 3 times higher and the wavelength is 1/3, right? In order to have more waves, a higher frequency, we have to have shorter waves. So this here will have more energy, this will have less energy. So right here, let's write more energy, and right down here, let's write less energy. We'll also see this in practice when we use some slinkies. Here, with amplitude, remember that is essentially the volume if you're talking about sound, or if you're again at the beach and we're looking at amplitude, we're thinking about the height of those waves that are about to crash on you. So this one has much higher waves, which means that they've got much higher energy and more force. So right down here, write more energy. Right over here, write less energy, right? Because it's got a lower amplitude. Same thing as if you're, at a concert, right? If the sound is turned way up, it's going to hurt your ears. That's because of the energy, right? So a higher amplitude, more volume, bigger waves, always going to carry with it more energy. So there's 2 general types of waves. Up here, we're going to talk about transverse waves. That's the most common type of wave. That's the waves that you're most familiar with in terms of drawing or seeing them depicted. That's also because it includes the electromagnetic spectrum. Down here, there's longitudinal waves. These travel a little bit differently. You are most familiar with them when it comes to sound. So we'll come back to longitudinal in a second. So transverse waves, they don't need a medium to move through. What that means is they don't have to travel through other matter in order to transmit the energy. So, for instance, this is especially important when we talk about electromagnetic spectrum, right? This is why light can travel through space. Sound, on the other hand, which is a longitudinal wave, has to travel through a medium. So sound does not travel through space. If you're in space and you were silly enough to leave your spacecraft and take off your helmet and try to yell, there'd be lots of other consequences, but nobody would be able to hear you yelling because there's no matter in space. Space is a vacuum. We took notes on that previously. Because space is a vacuum, there is nothing for that sound to bounce off of and move through, and therefore sound doesn't move through space. Light does, because it's a transverse wave. It doesn't have a medium or doesn't need a medium to move through. These waves move perpendicular to the direction of the wave. So meaning the wave moves up and down, right? If you're thinking about the ocean, the wave itself moves up and down, up and down, while the actual wave is moving side to side, right? We've got the trough and the crest going from down to up, back down and up, but the wave is crashing horizontally against the ocean. Same thing if you wriggle a slinky back and forth. Your hand is moving left and right, but the wave is traveling in this direction, right? The wave goes up and down, left to right, but the actual wave travels this way away from your hand. You see that? You shake it this way, the ups and downs go this way, but the wave itself moves that way. Light operates in the same direction, in the same way. The wave itself goes up and down while the wave moves horizontally. So examples can be ripples on water, electromagnetic waves, or a slinky. The most common one, and the one that we're most interested in, is the electromagnetic spectrum. Electromagnetic spectrum includes everything basically that can be given off by the sun. All of these are shot out by the sun. The electromagnetic spectrum includes everything from radio waves all the way down to gamma rays. And the reason that I say all the way down to is because radio waves, clearly depicted here, have a longer, what's the word we're looking for? Wavelength, a longer wavelength compared to gamma rays. So that means that the frequency over here is very, very low, and the frequency over here is very, very high. So if we remember about wavelength and frequency, higher frequency and shorter wavelengths means way more energy. So gamma rays, X-rays, and ultraviolet rays are the ones that we need to be really concerned about, right? Ultraviolet is what causes skin cancer, right? X-rays, that's why you wear a lead vest when you go to the dentist, right? To protect your body while your jaw is getting X-rayed, or that's why the doctor goes and stands behind the wall that is lined with lead while they shoot the X-rays, right? Gamma rays also even more dangerous because they have a shorter wavelength, a higher frequency. Over on this other side, though, infrared is used in our TV remotes. Microwaves, while dangerous, right? They can cook food. So if your hand was in the microwave while it was cooking, obviously your hand would get cooked. But that's why there's a door and there's those little metal screens. If you look at a microwave, you can see through it because there's a metal screen. The dots in that metal screen are too small for microwaves to travel through. Microwaves are pretty big. Their trough and crest is their amplitude is about the size of a softball, and so they can't get through that microwave. Radio waves are gigantic, right? That's why you've got big radio dishes on the top of TV stations and stuff, right? As they're transmitting, or not TV stations, radio stations, as they're transmitting those radio waves. They're huge. Their wavelength is, I believe, the size or the length of a football field. And so wavelengths or radio waves are not going to hurt you, right? Because their wavelength is so long, they carry so little energy that we can be around radio waves all the time. And we are, right? People have their radios on. We sit in a car that's got the radio on, and radio waves don't hurt us. Visible light is somewhere in the middle, right? And visible light is a whole spectrum. That's where the rainbow colors come from, right? Visible light is generally not harmful. However, if you get really close to a light and you stare into it for a while, you could go blind, right? Same reason why looking at the sun, right? The sun has a very high amplitude of visible spectrum of light coming out of it. And if you stared at the sun for a while, or if you went up close to a lamp and stared at it for 10 minutes, you at the very least would start to see spots and black spots that might be there for a couple of days. And at worst, you could go blind. So while light is generally safe, given the right amount of duration, it's dangerous. So because the electromagnetic spectrum, all of these are types of or examples of transverse waves. They can travel through space, right? They travel through space from the sun to the Earth. Our atmosphere protects us from most of these. Luckily, the gases in our atmosphere bounce off the gamma rays, bounce back the X-rays. Some ultraviolet rays are allowed through. That's why we can get skin cancer if we don't wear the appropriate sunscreen. And luckily, it lets light through. It also lets radio waves, microwaves, and infrared through as well. And we have different telescopes that can pick up that information. So with invisible light, there is a spectrum, right? Roy G. Biv. And plants like different colors on that spectrum. So the LED lights that we are using, the grow lights that we're using, give off a specific wavelength. LED grow lights generally give off red and blue, right? And so that's because plants most often absorb red and blue, and they grow best when they're absorbing the red and blue wavelengths from LED lights. So our LED lights give off mostly red and blue wavelengths. What that means is that it's giving off light, and the frequency or wavelength of light that those LEDs are producing appear to us, if they were to shine onto other things, they would appear red and they would appear blue. Because our eyes are able to detect the red wavelength as a color, right? That's why it's a visible spectrum. Infrared, microwaves, and radio waves are not visible. We can't see them, right? When you're listening to the radio in your car, you can't see the waves hitting the antenna. And if you go to the doctor or the dentist and there's x-rays being shot at your jaw, you can't see those x-rays coming through. We can detect them, right, using an x-ray machine, but we cannot see them. So the only ones that we can see, that's why it's called the visible spectrum of light, are Roy G. Biv, right? And so our LED lights will produce a red wavelength and a blue wavelength. So within the visible spectrum, it's a slightly longer wavelength and a slightly shorter wavelength, right? Obviously, gamma rays are still way shorter and radio waves are still way longer than the red. But within this spectrum, our lights are producing some of the longest light waves and some of the shortest light waves at the same time. So it's important to note that this side has way more energy. This side has way less energy. Even a radio wave that has a very high amplitude will have much, much, much less energy than a gamma ray with a very short amplitude, right? A very short height. Because these gamma rays are so frequent, getting hit by gamma rays means you're getting hit by a lot of those crests, which means that you're getting hit by a lot of waves. And just like at the beach, you get hit by a lot of waves, it hurts, right? Now, longitudinal waves are different. They have to move through a medium, so they have to move through water or they have to move through air particles, right? Especially when we're talking about sound. So a really common example that you can probably visualize is rather than waving a slinky back and forth, you pull a slinky back and then let it go, right? Oops. As you pull that slinky back and let it go, that slinky is going to contract and expand as it then moves in this direction. So you pull it backwards and release it going forwards, and all the waves travel forwards. Whereas with the transverse waves, when we moved our hand up and down, and the crests and troughs went up and down, the wave still moved left and right. But in this case, you can see here that these sections right here are a little bit more closely expanded, while over here, they're a little bit more spread out. And you can see that in this blue as well. So where the lines get closer, that means that they are more frequent. That would be a crest versus a trough over here of the wavelength that was going to whiplash at you. Same thing visualized right here with the speaker, right? With the speaker, you see that there's not only different amplitudes, different heights, but you see that there are waves that are closer together and further apart. And so as they get closer together, that would be the crest. As they get a little bit further apart, as the dip goes down, that would be, right, as they get further apart, that would be the trough. So sound waves, the vibrations move in the same direction. So longitudinal waves have to happen in something like a gas, which is why we can talk on Earth and we can hear each other, or even underwater. If you yell, you can hear each other. But because sound waves travel less successfully through the density of water, you can't hear each other quite as far. But obviously, whales and other animals can communicate underwater. And if you go in the swimming pool and you and a friend are at the bottom, you can still hear each other. So, just to quickly summarize here, what we've learned is that waves have different repeating patterns, right? They all have a crest, which is the top, a trough, which is the bottom. They have a wavelength, which we measure from the crest of one to the crest of the next. And they have an amplitude, right? The higher the height, the higher the amplitude, the more energy. The longer the wavelength, the less frequent the wave, and therefore the less energy. But if we shorten this distance and the wavelength gets shorter, the frequency will also increase, which means that the energy will increase. So we see this here with high frequency versus low. We see low amplitude and high amplitude. High frequency, high amplitude, both have more energy. I like to think about it, the most easy way to think about it is at the beach, lots of waves hitting you, big, huge waves hitting you. Then we recognize that there are longitudinal waves. They move in the same direction that the wave pattern is occurring, right? So the waves get closer and further apart for the wavelengths, and they get released. The energy gets released in the same direction. The ones that we're most familiar with and most interested in are transverse waves. The wave goes up and down while it moves horizontally, and specifically the electromagnetic spectrum with the visible light waves, which is what we're using with the LED lights.